Okay. So now remember, we've got our group papers that are due on Wednesday. They're due. I want you to hand in a hard copy. I think if you look at that checklist thing that I gave to you, I think in the direction, I don't know if you looked that carefully at it, in the directions there it said something about hand in a copy of that with your paper. You don't need to do that. Just give me your hard copy stapled together. It's a letter, so you probably ought to sign it. Everybody in the group should sign it at the bottom, and sincerely, whatever, and then sign your name. And hand that in. And also, one person in your group needs to upload a Word document or a PDF version on Turnitin.com. Okay, that's due Wednesday. All right. So for tomorrow, gateway test. First thing that we should probably focus on is page 333, the basic formulas. Make sure that you know those. Now, it would be potentially useful to know, some other ones. For example, on page 333 is the antiderivative of secant squared, is tangent. And of course, that's because the derivative of tangent is secant squared. But likewise, cosecant squared, the antiderivative would be negative cotangent. It might be nice to know that one. Now, it's not going to be on the gateway test necessarily, unless there'd be another way of doing it. So you won't have to have memorized that one for the gateway test, but it might not be a bad thing to know. Now, I can think of at least one, and there's probably some others, that if you knew a little more than just the basic formulas on page 333, could come in handy. For example, look at this problem. If I had the antiderivative, I think this was actually in one of our homework assignments. If you had the antiderivative of secant tangent dx like this, I think we did this one in our u substitution homework. Now, what a lot of people did is they went with a u substitution on this one. But before you do the u substitution, you have to do something else. Now, what is the antiderivative of secant x tangent x? Secant x. Right? I mean, because the derivative of secant x is secant x tangent x. So therefore, the antiderivative has got to work backwards. So if you knew that, that would be a very easy one to do on the gateway test. You just write secant x plus c and you'd be done. If you didn't recognize that, then what a lot of people do on this one is they change everything into sines and cosines. So this would be 1 over cosine x. Tangent would be sine x over cosine x dx. So this would be sine x over cosine squared. And so what would we let u equal here? Let u equal cosine x, the inside of the bottom. The du would equal negative sine x dx. Move the negative over to this side. So your substitution would be a u squared on the bottom. Sine x dx would come out as a negative du. So this would be u to the negative 2. So you raise that up to a negative 1, divide by negative 1, and cancel this. And so you just have 1 over u, or u to the negative 1, plus c. And then you put the cosine back in. 1 over cosine is the same as secant. Now you could just leave it like that. If you went the u substitution route, you could just leave it 1 over cosine x plus c, and that'd be fine as your final answer. Okay? But if you happen to know that formula, you could have just done it without even doing u substitution. Somebody in the other class asked, do you have to show work? Is it okay to just, on the gateway test, just put secant x there? Absolutely. Okay? Because that is the right antiderivative. If you knew it, that's fine. So know those basic formulas. If you knew, if you can remember some other ones, you never know when that could be helpful. All right. Second thing was our u substitution. Okay? Now, a couple things that we talked about with u substitution was we looked at the inside as far as what to pick for our u. We looked at the denominator, the bottom of a fraction is what to pick for u. And the most probably overriding thing of what to pick for you is you hope that the du is also in the problem. Right? I mean, that's the real important part of that, like the one we just did. Okay, the reason that the u substitution worked well on that last one is when we let u be the cosine right here, the du, the sine x dx, was setting right there. That was the key. That's why u substitution was so good on that problem. All right, so those are the things we look for. Now, there were some special situations that arose. One situation that arose, kind of lost track. I know I had a couple of them, but I can't remember now which one I was going to mention. Okay, well, if I think of it, I'll... But here's one of them, okay? What's going to happen on a situation like this? What are we going to do there? We're going to have to solve for x. Oh, I know the thing for x. Okay, I'll do that. We're going to have to solve for x. We're going to let u be the bottom. The du will be negative dx, which we can just move over. So when we sub that out, we're going to get u to the 1/2. We're going to get a negative and a du. And then we're going to have this extra x. Well, when you get an extra x, a lot of times, not always, but a lot of times what you do is you solve for x. So in this case, you add the x over here, you get the u over here, and we end up with 1 minus u, subbing that out. Now, what advantage did we just gain there? We can distribute that. You could not distribute through that power, that 1/2, but you can distribute this, and now you get your fractional powers, and you can finish from there. Okay? So that was kind of a special scenario that came up with u substitution sometimes. Oh, okay, I remember what the other one was. Okay? What if you get, this was an example of one we had. X plus 3 over 1 plus x squared. What are you going to do there? Split them up? Split them up. This was one of those problems we had where we said you split that up. This would be x over 1 plus x squared dx plus 3 over 1 plus x squared dx. Now, what happens on this one? What are you going to do here? Let u be the bottom. Because the thought process here is if I let u be the bottom, matter of fact, that's the thought process you should have done in the beginning. If you're sitting there saying, hey, I didn't see that split up thing, here would have been your thought process. You just said, well, if I let u be the bottom, 1 plus x squared, the du is going to be 2x dx. I don't care about the 2. We'll take care of that, but I got an x dx, and that's sitting right there. Well, if you thought that originally, you'd be saying, well, I got a 2x dx, but I don't have an x dx. I got an x plus 3. The plus 3 is the problem. Well, the plus 3 can be split apart. Now, when you have just the x dx, that works just fine. And then what are you going to have over here? You're going to have a 3 arctangent. Okay? So that was one of those things that happened where we split it up. Now, you don't always split up a situation like that, though. What if you had this? Let me change it just a bit. What if I had... What if I had this? Now, it doesn't look much different than this one. What are you going to do on this one? How do I cancel x plus 3? Like factor? I don't think that factors. X squared plus 6x plus 1. Yeah, I don't think that would factor. If it would, that'd be nice. You're right. That's a great point. Look, that'd be one thing to look at. See if you can factor and cancel an x plus 3, but it doesn't. Ideas? What do you let u equal? Let u be the bottom. Now again, what's the thought process? The thought process would be if I let u be the bottom, what's the du? 2x plus 6. Take out a 2, you've got an x plus 3 dx. which is what's setting right there on top. So that would have been the thought process. About the only thing I can think of is let u be the bottom. It gives me a 2x plus 6 dx. Take out the 2, which would mean move it over to here, 1/2, and then I get x plus 3 dx, which is setting right there. So it ends up being kind of a natural log situation. Okay? So those are just some of the more difficult or a little more challenging things that happen with U substitution. You know, some U substitution are just pretty routine. You pick the U, the DU's there, and away you go. These were some of the things that happened to you that were a little more challenging. Okay, the thing I skipped that I meant to do, let's do it now, and that would be the idea of definite integrals. Now, somebody asked in the other class about, is this graded the same way as the gateway test before? And it is. The first gateway test we did, not that quiz we did here recently, but it's all right or it's all wrong for the most part. You got to get 8 out of 10. You get 8 out of 10 on this first try, you get 30 out of 30. Then you can have 2 tries to get a 28 out of 30. And then you can have 2 tries to get 26 out of 30. Then you can have 2 tries to get 24 out of 30, and so forth, so on. Probably need to have that done before the end of the term, which would be 2 weeks from tomorrow. Okay, should get it passed by then. If you haven't gotten it passed by then, you haven't tried very many times. Okay, because you can easily get 6 more attempts in those number of days. Okay, and you should pass by then. So either you haven't tried very hard or you're just not going to. And if you don't want to, if you get 2 out of 10, you can take a 20%. That'd be 6 out of 30. That's what would go in the grade book. Okay, if that's what you want to do, then you don't, you can just stop right there. All right. So that's how we graded. Now, one of the things that hurt people on the first gateway was that simplifying, the algebra that you had to do. You don't get into a lot of that with these. However, with the definite integrals, that is an issue. Let's take a real easy one here. If you had the antiderivative from 1 to e of 1 over x dx, right? Well, what's that one? What are you going to get there? ln absolute value of x, right bracket, 1 to e. So you get ln e minus ln 1. That's not good enough right there. That's not good enough. Okay? What's ln e? ln 1? 0. Final answer in this one had to be 1. Yes?
If that wasn't e and it wasn't 1, and it was like 5 and 3, would you have to simplify it or just...
We're going to have one here a little later today. If that would have been the integral from 3 to 5, ln 5 minus ln 3 would have been okay. You could have stopped right there. If you check that on your calculator, it's actually what? It's actually ln 5/3 because of one of the properties of logs. You would not have to do that. Okay, but if you know that, go ahead and do it. That's fine. Okay, but ln 5 minus ln 3 would be good enough. Now, same thing with a cosine here. Let's say we had cosine x dx from 2 to let's say we had this. Okay? Antiderivative of cosine from 2 to 3 pi halves. Okay, well, what's the antiderivative of cosine? From 2 to 3 pi halves. Well, that'd be sine of 3 pi halves minus sine of 2. Now, what's sine of 3 pi halves? -1. Sine of 2 is just some decimal we don't know. So you wouldn't simplify the sine of 2, but you would simplify sine of 3 pi halves. Anything that's pi, pi halves, pi fourths, pi sixths, pi thirds, you should be able to do those. Okay, those are just things we need to be able to do. Now, if you got to draw triangles to do it, you got to make yourself a unit circle to do it, whatever. That's what you'd have to have. Okay? So if you need to review those things, review those things. You might get some with some ugly decimals, like that last quiz we had. All right? You might get some that get into some decimals. Yes, you've got to simplify those. I'm not going to make them horribly ugly. We got one we're going to practice today that gets a little bit ugly. We'll talk about what happens if you get one of those. You have to review a little 6th grade, a little middle school math maybe to do that. But Okay? All right. That's right. You guys shouldn't have to be. You should not have to be responsible for 6th grade math. All right. Integration by parts. Formula. Obviously, you have to remember. One of the biggest things you got to remember is when to do it, because oftentimes the people that struggle with these try to do integration by parts way too much. Probably 3 times tops on the gateway test. Probably not even that many. Okay? There wouldn't be more than 3. So if you find yourself doing the UV, DV thing all the time, it's not like you have a choice. It's not like, you can use your favorite methods. Like, I think on this one I'll do integration by parts. I like it better. I'm going to do it on all of them. It doesn't work that way. Okay? It's not like you have a choice. I mean, I can't think of anywhere you could do U substitution or you could do integration by parts. You have your choice. It's not the way. Now, sometimes you do integration by parts, and then when you get to the end, you still need U substitution or vice versa, but it's not like you just have a choice. Okay? So a typical one, just an easiest of all easy ones, and we'll get doing. This is the very first one we did, is one like this, x e to the x. Now, one of the things we usually think of if it needs integration by parts. How do you recognize it?
Function family.
It uses Liate to tell what you pick for u, but it's a mixture. 2 different function families. It's a mixture of functions. Okay? It's usually going to have an algebra with a trig, or an exponential with a log, or whatever. There's no obvious U substitution that you can do. Okay, that's the first one you would think of. And of course, the first thing you should think of is, do I need any of it? Can I just do a straight antiderivative? Okay, that's the first thing you ought to try. And then, is it a U substitution? And then, only then, if it's not, if it looks like this, usually it's a product. Most of the time, we're going to do an example of one that doesn't look like a product, but it really is a product, and you'll see here in a little bit. So in this case, we got algebra and exponential. Liate would say use the algebra for your u. So u equals x, dv equals e to the x dx. So du is a derivative, that's dx. Don't forget when to do the derivative on the u, and on the v you do the antiderivative. That's an important distinction. So now we follow the formula, u times v minus the integral of v du. That one's about as easy as it gets. The whole point of integration by parts, much like U substitution, is to turn it into a new integral that's easier to do. Hopefully one you can do with basic antiderivatives. Now sometimes we do an integration by parts, and this one ends up being a U substitution that we have to do. Could be the other way around, but probably not. I think in the book, one time we had a homework problem where they said, do this U substitution, and then it ended up being an integration by parts when you did the U substitution. I'm not going to give you one of those. But it could be one where you do your integration by parts, and then you get to here, and this new integral needs a U substitution on it. Okay, that could happen. But again, not very often. Most of the gateway ones are going to be pretty straightforward. Integration by parts, do it, you're done. U substitution, do it, you're done. Basic antiderivative, do it, you're done. There wouldn't be very many where you have to do more than one of those things. Okay, that antiderivative is, okay, that right there. So that's just a run-of-the-mill integration by parts. We talked about those ones you have to do it twice to get an answer. May happen that'd be the most you'd have to do. I think the example we did is if you had x squared here, that would have come down to an x e to the x. You do it again. We talked about the one that circled around with the sign in it. You did it twice, and then you got back to the same thing you had, and you had to kind of solve. That's not going to be on. That's not going to be on. Okay, so that's a pretty good summary right there. Okay, so let's get out that work that you guys did in class on Friday. How far did we get on checking them?
We need to do 9.
We still got to look at 9, 10, 11? Okay. All right, so in class on Friday, we had gotten down through number 8. And I gave you these 3 to finish up. All right. So, thoughts on number 9? Oops. What could we do on number 9? This one is an integration by parts. And this it doesn't quite look like one because it's not a product, but and remember we want our integral to be u dv. We want it to be u dv. So I mean we need those two things. So it's typically kind of a product sort of a thing, but this really is a product, right? It's ln x times x to the negative 2. Now, it's not a u substitution because what could you try? You could let u be the bottom, x squared. Well, that gives you 2x dx. You got an x dx there, and there's no x sitting there, okay, that you can deal with. There's an ln x. So then you might say, well, what about ln x? Matter of fact, let me cover up that 2 right there. Well, if that 2 was not there, okay, if this was just an x down there, what would you do? You'd let u be natural log x, right? Because the du would be 1 over x dx, and then that 1 over x dx is sitting right there. So then you might say, well, why not do u equals ln x, and then you do 1 over x dx, and then you have an extra x down here. And we've handled extra x's before. Well, it's not really an extra x, it's an extra 1 over x. And then you can try it, and it doesn't solve out very well. It doesn't work. Okay? So it turns out really the only thing you can do is make this ln x times x to the negative 2 dx. This is log, this is algebra, so we're going to want to let u equal this. So we're going to let u equal ln x, and we're going to let the dv be the x to the negative 2 dx. Okay? And if you go through and do that, okay? If you do that, it ends up looking like this. Derivative of that's 1 over x. The antiderivative of that, raise that up to negative 1, divide by negative 1 would be this. Take u times v, those two, and multiply them together would be that. You got to be careful with your minus signs here. You'd have minus the integral of v du. So these two multiplied together. Now this is a 1 over x times a 1 over x. That's 1 over x squared with a negative. So there's a negative x and negative 2. Now those two negatives would cancel. But you're going to get another negative when you do this antiderivative. You raise that up to negative 1, divide by negative 1, so you end up with you do in the end end up with a minus there, x to the negative 1. Now you could factor out a 1 over x there, or you could put the ln x on top and combine them with common denominators, but you wouldn't have to do any of that. That's just rearranging. It's not really simplifying. So that'd be fine. Okay? So that's an integration by parts. All right, what about number 10? What'd you do on that one? This gets into something we didn't talk a whole lot about. I think we might have done one similar to that. Could take out the 3. Okay, bring that out in front here, yep. What about this bottom? It looks like an arctangent, almost, right? Arctangent's 1 plus u squared, right? So what could the u be? 2x. So the smart thing here is to think of this down here as 2x quantity squared, and now this is an arctangent. If we let u equal 2x, matter of fact, you may not even have to let u be the 2x. You may just look at it and say, hey, that's going to be an arctangent, and I'm going to kick out a what? No, not a 2. 1/2. We're doing antiderivative, so you have to kick out a 1/2. Okay? Now, if you don't see that or you're uncomfortable with that, then just let u be the 2x, and you get du equals this, oops, dx. And now you can see where the 1/2 comes from. That's because you moved that 2 over there. All right? So now you've already pulled the 3 out, and then you get a 1/2 out here. Okay, when you take out this, so that's all gone. And now you got 1 over 1 plus u squared. So that is arctangent. So we have 3/2 arctangent u, which would be 3/2 arctangent 2x. Okay? Now, I want to show you, let's go ahead and we'll get down here to it. Okay? So it ended up looking like that. So you got 3/2 arctangent u, which would be arctangent 2x, and you get that right there. Now, another one that we don't see very often, but it could be on there just from, like I said, there may be one or two that are fairly difficult, or something just a little extra in it. But what if you had 9 plus x squared dx? What if you had that? Now, if you had an x, now again, if you had an x up here, then that'd be a u substitution. You be the bottom, you get your x dx to take care of that. Okay, so then it's not a big deal. But you don't have an x up there. You have this. Is there any way we could turn that into a u substitution? Or, I'm sorry. Is there any way we could turn that into an arctangent? Arctangent has to be 1 plus something squared. Well, yeah. I'm gonna do that one step at a time. I'm gonna take a 9 out of the bottom, which would be the same as a 1/9. Okay, I can take a 9 out of the bottom here. Tell me what I would have. 1 plus 1/9 x squared. Now you got to get a little tricky with your algebra there. But I can take a 9 out of this right here. I can always make this, if I get a constant plus something squared, I can always make it into a 1 plus something squared by doing that piece of algebra right there. Now, this 9 sitting here is just what Chris said. That is a 1/9 out in front. So I've now turned it into this. Okay, I've now turned it into a 1 plus 1/9 x squared. Now, what's another way to think of 1/9 x squared? 1/3 x quantity squared. So what can I let u equal? I could let u equal 1/3 x. And I would end up with a 1 plus u squared there. I'd end up kicking out a 3. I'd end up with a 1/3 dx, move it over to 3. So I'd end up with a 3/9 out in front with a 1 plus u squared. So anytime you have a constant plus something squared, you can turn that into a arctangent. Now, that's assuming you don't have an x or something else up here. Right? If you have something else up here, then that changes it. Then it becomes probably a basic u substitution or something like that, and not an arctangent. Okay? Probably not going to be one of those. If there was, that would be one of the hardest ones that I would have. One that if you missed it, it still wouldn't cost you from passing the thing, if you did everything else right. Okay? All right. And then number 11 actually was an easy one. I think when I made this up, I think I intended to do 10 of them, and then we had time, and so we did an 11th one. Pretty easy u substitution, right? Let u equal to 2x cubed. That gives you the x squared out in front, dx, and so that's a pretty just straightforward. Pretty much a straightforward u substitution. Okay? All right. Now, on the website, I'm trying, everybody's here today, so it shouldn't really be an issue. I've got that PDF in the files section. I've also got it up here. I'm trying to get the one we're going to do today. I'm trying to get that one up there too, but we'll do it here in class. It's not like you'll need it, but it hasn't uploaded for me very nicely. I've also got this link, which takes you to that antiderivative practice link. If you go down here a little farther, okay, antiderivative practice number 1, I believe it is, takes you to this right here, and there's your 8 little tests right here. It's got the solutions worked out. I think it's got 8 problems on each one. That would be a good thing to be working on if you need some more practice. Okay? All right. Let's go ahead and work on a few here today. So, here are your first 2 right here. Okay, there's 1 and 2.